Okay, it looks like our numbers have stabilized a bit and we're about a minute or two after. So welcome everyone. Eric, could I just get a quick sound check? Eric or Alex? Hearing me okay?
Sounds good.
Excellent.
Yes, you can.
Excellent. Thank you. Thank you. Welcome everyone to the Riparian and Wetland thematic climate engine training that we have scheduled for today. I'm sure many of you have received emails from me and a number of other folks advertising this. This is a follow-up from an introductory training that we did back in June. And originally we had planned to do these in October, but due to the lapse in appropriations, we had to do some rescheduling. But we're happy that we're able to get them going today. In a couple of weeks, we'll have an upland training. And then at the end of January, we will have a drought and vegetation productivity training. So I'd just like to kick things off and introduce myself before I turn it over to the folks at Climate Engine. So my name is Tim Asau. I work out of the National Operations Center, where I'm the Remote Sensing Coordinator for the Assessment, Inventory, and Monitoring Program, or AIM. And I coordinate efforts to integrate remote sensing into the AIM program, and we do that in a number of different ways, including research collaborations, with which the Climate Engine collaboration is one of those. And I just wanted to give a little bit of background as to how some of this came about, and why we think this collaboration is important. So the origins of this collaboration way predate my own time within the agency, and they started with Sarah Peterson, who began this work in the Nevada State Office in the BLM. She's now moved on to the USGS. And then Alden Shellcross picked up some of this work as well and championed it in the state of Montana during his time there. And he continues to be connected through this work with Climate Engine as well as Riverscapes. And finally, Nikki Cutler in Nevada also continued Nevada's support of this information. Then several BLM headquarters programs invested in this collaboration as well and made it a bit broader. So this was not only AIM, but also the range and aquatics programs. And there's also several people, several key players associated with that. Scott Miller, Paula Cotillo, Emily Kajirgis, Justin Shirley, and Jessica Phillips, to name a few. Okay, so why this collaboration? I would argue that monitoring is a common denominator across all of these BLM programs. And within AIM, integration with remote sensing, as you see highlighted there, is one of our half a dozen priorities. And to achieve that, we have three primary AIM remote sensing priorities. And those are scientific relevance, communicating data and workflows for decision makers, and fostering collaboration. Collaboration is key for a lot of different reasons. And one of those is we just have limited bandwidth for many of us within the BLM. And finally, I want to sort of talk about why I think this collaboration is significant. And so we've all heard this idea of, data to decisions. That sounds great, but there's a lot of challenges associated with that. And for those of you that have done remote sensing for a long period of time, like myself, I can't stress enough just how much information is available through Climate Engine. And this is not just from the derived products from remote sensing, such as fractional vegetation cover. Those are massive data sets in their own right. But there's also a ton of various forms of satellite data alongside that. A lot of climate data, a lot of other remotely sensed data. Collectively, we tend to call that big data. Now with this comes a challenge, and I won't go into this too much, but this idea of getting data into a digestible form for our managers to make decisions is challenging. And Climate Engine has been doing a really nice job of helping us out with that. Today's work is going to focus mostly on Climate Engine reports and the Climate Engine app. But there's also an API, and we're also collectively are working on some other programs for our power users that we won't go into today. Okay, so with that, I'd just like to mention one other thing. In today's training, if you prefer to follow along and not sort of branch out and do anything, please do so. There'll be the folks at Climate Engine do a really nice job of embedding links in these in their slides that will take you to those examples in the Climate Engine app or based on some report. Okay, so with that, I'm going to turn it over to Eric Jensen, who is a research scientist with the Desert Research Institute at climateengine.org. Eric, take it away.
Excellent. Yeah, thank you for that setup, Tim. And Yeah, we're excited to be here. Thank you all for joining us for this session, monitoring riparian and wetland resources using satellite data in Climate Engine. Just a few housekeeping items before we get started. We are recording this session, and so just keep that in mind. And you should, if you registered for this session, receive the recording immediately following it. Like Tim mentioned, to follow along with this session, following the links, you will need a Climate Engine account. So I sent an email earlier this week, and hopefully folks were able to follow along with that. We won't be able to support creating an account right now, but yeah, that will help you follow along. Please add any questions that you have during the session into the chat. Tim and Alex and I will be fielding those in the question and answer portions of this session. And in general, we'll be covering a lot of topics. This session will move fairly quickly, and that's by design because we will be recording it. And so we encourage you to review these materials after the training to figure out how to integrate and apply these concepts in your own work. Okay, so as Tim mentioned, this session is situated as the first of our kind of resource-specific sessions that we're providing for the BLM on using Climate Engine. 2 weeks from today, we'll have a session on upland ecosystems, and 3 weeks from today at the same time, we'll have a session on drought and vegetation productivity. So we encourage you to sign up for those sessions as well. They will be quite different from one another. They will focus on different examples, and I think they're pretty additive in terms of giving you an understanding of how you can apply Climate Engine in different contexts across BLM. We are assuming that you attended the Climate Engine Basics training, either attended or viewed that training. So if you did not attend that, this might move especially fast, and we would encourage you to go back and review that, and then that will help you keep along with this training, which is kind of more intermediate type training. So a little bit about us. I'll introduce myself and then hand it over briefly to Alex to introduce himself. I'm a research scientist at the Desert Research Institute and on the development team of Climate Engine, which you'll be hearing a lot about today. I lead our work with the Bureau of Land Management and am really tend to focus on developing software for operational data for resource management decision support. And so the work that we're presenting on here is really a big focus of the types of things that I work on. And then I get to work with Alex quite a bit on our work with the National Park Service as well, which is a somewhat related project. And with that, I'll pass it to Alex.
Hi all, it's great to see the turnout today. I'm an ecohydrologist at DRI, and I have research that focuses on kind of integrating Earth observations, field measurements, and hydrologic analysis and modeling, with a focus really on riparian wetland systems and other groundwater ecosystems as well. And a lot of what I do is trying to think about cross scales, thinking about how we can kind of develop evidence and understanding that can guide development of practical tools for monitoring watershed condition and prioritizing management actions.
Excellent. Thank you, Alex. All right. We've got 2 hours with all of you. After this introduction, we're going to jump into some background and overview and kind of set the stage for why we want to apply satellite monitoring in riparian and wetland contexts for BLM. We'll highlight some new functionality that we've added to Climate Engine since the first set of trainings that are really going to drive a lot of what we're doing in this session. And we'll have then a really nice overview by Alex of core riparian and wetland data sets and indicators, and we'll leave some time for question and answer. Then we'll move into a BLM practitioner highlight with Wyatt Fereday, hydrologist from the Carson City District Office, where he'll highlight some examples of using Climate Engine in land health assessments and other uses. And the last hour and 15 minutes will really be focused on uses of the Climate Engine web application. And so we'll have a first demo on creating maps of riparian status and trend. The second will be more of a time series analysis of impacts of groundwater use. And the third example will be kind of a capstone, pulling everything together into an assessment of riparian restoration effectiveness following wildfire. And then we will close. We try to have question and answer kind of peppered in throughout, so there will hopefully be opportunities for some discussion as well. By the end of this session, we hope that you will have a better understanding of some of the core satellite and contextual climate and hydrology data sets that are available within Climate Engine for riparian and wetland decision support, that you'll have some more workflows that you're able to implement in the Climate Engine web app to analyze status and trends in riparian and wetland resources. Importantly, that you'll have increasing confidence in your ability to apply satellite indicators to produce maps and figures for decision documents, resource monitoring activities, and other reporting processes. And then importantly, that you'll be able to access the recordings and supporting materials so that you can study them and integrate them into your work at a later time. So Climate Engine, we began more than 10 years ago with support from a Google Earth Engine grant that got this project off the ground. But in the 10 years since then, we've really been supported by federal agencies in the US, and BLM has been an important partner, as Tim mentioned from the outset. We focus in general on providing tools such as our app, API, and reports that make cloud-based processing of large satellite and climate data sets more accessible to a wider range of audiences, especially resource managers and applied researchers. And we really focus on integrating best available kind of decision-ready data sets into Climate Engine. As Tim mentioned, our project goes back with the BLM goes back to 2015, and we've in the past 3 years expanded that project and rolled it into a larger agreement with the National Operations Center and headquarters with program support from Assessment, Inventory, and Monitoring, Aquatics, Range, and the Nevada State Office. And our main focuses are to develop tools that are relevant and useful for the BLM, integrate priority data sets into Climate Engine for the BLM, support integration of Climate Engine tools into BLM software systems and processes, to provide Climate Engine training and support for BLM staff and partners, and to conduct applied remote sensing research and needs assessments to support BLM operational needs. So a pretty wide scope of trying to bring remote sensing research into operational use. So I think it's important as we pivot to talking about riparian and wetland systems in particular to just look briefly at the kind of guiding policies for aquatic resource management across the agency, being this manual that we pulled from. And this manual sets out guidance for informing land use plan decisions, implementation decisions, and adaptive management in the decision guidance section. And throughout this document, there are requirements that staff use, identify measurable and quantifiable desired outcomes, have clearly defined and measurable outcomes, have specific resource condition thresholds and standardized monitoring. And then on the monitoring side, it calls out specifically having a strategy for collecting priority information that should be outlined in monitoring plans, including integration of remote sensing tools. So throughout this policy document that was updated in 2023, there is a lot of emphasis on quantitative data. And that's really one of the strengths of satellite data, is that the same types of methods can be applied consistently in any location. And so some of the ways that we think that remote sensing supports riparian and wetland management activities for BLM is by providing historical context. Satellite archives go back more than 40 years in some cases, back to the mid-1980s, which is pretty extraordinary at this stage. Satellite data sets provide consistent data that can be applied in the same way in any location. It can support analysis at multiple scales. The data are frequent, so you don't just get a yearly snapshot or a static data point, but you get sub-yearly, often many times a year, observations. In Climate Engine, we incorporate climate and hydrologic context into the data sets that are available, so you can investigate drivers of the vegetation response that we're observing in the satellite data. Depending on your question, the spatial resolution of these data sets can be a strength or a limitation. Most public satellite data that we'll be talking about today will be 10 meters to 30 meters, which, depending on your question and your area of interest, could be limiting or could be adequate. And then in Climate Engine, we also try to provide important contextual layers like land ownership, land cover, and so on that can support interpretation and use of these data. Climate Engine is being applied in a number of different contexts. So this is an example of the use of Climate Engine to quantify degradation of a spring in a land health assessment that the Carson City District Office used several years ago. And this was important because it not only documented the declining production of the spring, but also accounted for the climate, which was not, in this case, driving that vegetation decline. And so they were able to more confidently attribute the degradation of this system to higher utilization rates as a contributing factor for not meeting proper functioning conditions. So we'll give more detail on, much more detail on the riparian and wetland context and some specific analyses. But I do want to introduce some new functionality that we have available in Climate Engine since our previous session last June. And these were all developed with support and really kind of with the motivation of providing more useful tooling to audiences like yourselves. So the three new features we have are high-resolution base maps, categorical raster layer overlays, and categorical data masking. So let me explain each of these through a slide. The high-resolution base maps, we have 6 layers available. 3 of them come from the National Agricultural Imagery Program, or NAEP. We have NAEP True Color, False Color, and NDVI. We also have historical imagery from the University of Montana, and we have 3 high-resolution 1-meter topographic data layers from the USGS 3DEP program, and those are slope and hillshade. And these layers are important because the satellite data that we're often analyzing, while they go back many, many years, they're often somewhat coarser in their spatial resolution. And so being able to match an analysis period that you're interested in using Landsat or Sentinel-2 with a high-resolution aerial image that you can interpret is really useful to be able to kind of interpret what you're seeing in the satellite data. And we'll see that throughout our examples. The second new feature we have are categorical raster overlays. And so this is adding more static kind of thematic layers to Climate Engine. So we now have the National Land Cover Database, the National Wetland Inventory, Surface Management Agency for land ownership, the Valley Bottom Extraction Tool, indicators of groundwater dependent ecosystems, and World Cover, which is a global land cover data set. And so these can provide useful context just as to who manages a piece of land as you're investigate some of the maps in Climate Engine. And then we put them to work in this new functionality we have for categorical data masking. And so here we're applying these categorical raster layers to be able to focus or subset your analysis on specific land cover, topographic, or other kind of areas on a map. So for example, in the first session in this series, we created NDVI trend maps, and you can see in this middle panel where we're now able to use the Valley Bottom Extraction Tool from Utah State University to create effectively a network map of trends in June, July, and August Landsat NDVI just for the valley bottoms. And we can apply this uniquely to the low-lying or elevated valley bottoms. So it really allows us to focus our analysis. We can also apply this functionality to time series analysis. And so in this figure, you can see pulling out remote sensing data differently for the same area, but for National Park Service versus BLM managed land, or in the context of this session, we could apply an analysis to look at the difference between NDVI in the elevated valley bottom from the low-lying valley bottom. So we can, with much greater detail, subset the landscape to focus on the areas that we're interested in. And you'll get a much better handle on this through the course of our demonstrations. So with that, we're going to move into an overview of core riparian and wetland data sets and indicators that Alex is going to lead us through. So I'm going to stop sharing and hand things over to Alex. And Alex, you are muted.
Thanks, Eric. All right, well, I'm going to spend a little time talking about the core data sets in Climate Engine that are useful for monitoring riparian and wetland resources. And so riparian and wetland resources are quite distinct from other systems. And so I think it's important for us to spend a little time here talking about what the data sets are that are most useful and also how to best apply them. And so we have, a few different types of data sets that are helpful for these types of analyses, mapping extents. And as those of you who work in these systems will know, mapping riparian and wetland systems is not a trivial task. And so having these data sets readily available can be extremely useful. But you do have to be aware of kind of what they are actually mapping and then think about whether they're appropriate for your context. One data set that I want to mention that we don't have in Climate Engine is the National Hydrography data set, which is incredibly useful for getting information about the locations of streams and water bodies and springs. But you can pull those in as polygons into Climate Engine and kind of use some of that data in some of your workflows. We also have data that's Earth observation data sets that provide gridded weather observations and drought data that can be really relevant to understanding dynamics in these systems. And third, we've got remotely sensed data that provides information on vegetation and water. And so we'll talk through all three of these types of data sets in a bit more detail. We're going to start with talking a bit about the mapping, the extent data sets. One of the most useful data sets that we have is the National Wetland Inventory. This provides detailed information on the abundance, characteristics, and distribution of U.S. wetlands and riparian areas. And BLM has been a major driver of updating these data sets. And so we have high quality mapping from many, although not all, BLM lands. More broadly, mapping detail and coverage can vary quite widely. On the right here, you can see a map that shows where NWI was last updated, and it can range in some cases from the 1970s as the last update to other areas that were updated last year. And so because of that, the quality of the mapping and the extensiveness of the mapping can be quite different depending where you are. In Climate Engine, we have a simplified version of this that simply it's a raster, categorical raster that shows the wetland type, but it doesn't contain the type of detailed wetland classification data available elsewhere. So you would have to go to the Fish and Wildlife Service's own mapping program to access more detailed information about these wetlands. Our second mapping extent data set that's quite helpful, as Eric mentioned, is the valley bottom extraction tool, which has been developed by the Riverscapes Consortium. And its development has been significantly supported by BLM as well. VBET identifies and delineates valley bottoms using a hydrogeomorphic approach. And valley bottoms can be classified as either low-lying, which is shown in blue on this map, or elevated, which is shown in yellow, based on the relative topography and hydrologic connectivity. In Climate Engine, again, we've got this as a categorical raster, so it can be used as a mask. And again, the mapping quality can vary quite a bit as it relies on the accuracy of the underlying DEMs, the digital elevation models, and NHD flow lines. And it typically performs better in large streams than it does in small headwater systems. The third mapping extent data set that I want to touch on is the National Land Cover Data Set, or NLCD. This is a USGS product, provides nationwide land cover classification. There are 16 different land cover classes, and they include woody wetlands, emergent herbaceous wetlands, and open water. It's been recently released as an annual product going back to 1985, but we only have the most current version in Climate Engine to provide kind of a masking layer of current wetland locations or other land cover locations. It's also a 30-meter product, so it's coarse resolution, and so that means it's somewhat limited in how well it can delineate riparian zones, but it does have value for capturing kind of a wide range of land covers and uses, and also for analyzing change over time if you have access to the full time series. It's also important to know that if you are using this data set in western wetlands and valley bottoms, that there is frequent confusion between wetland classes and the pasture hay class. And that's something you have to look out for. There's commonly, wetlands can be classified as agriculture or vice versa. So you might be wondering, if you're going to map these systems, which of these data sets you should use. And the answer is, of course, that it depends. And it depends on kind of what definition you want to use to define your regions of interest, and also on the mapping quality of a given data set in the location you're interested in. So to illustrate this, I have two examples. The first is a low-lying valley we can see here on the White River north of Ely, Nevada. And in the imagery, you can see an extensive graded wetland complex that's mostly on BLM land, although there's also some private grazing land on the southeast corner, or at least it's fenced in area and private land. You can see, kind of look across our different mapping extents and see quite a bit of differences. The NLCD data set maps mostly shrubland, picks up some woody wetland in this light blue, and then picks up some emergent wetland and pasture hay down on the southeast corner. VBET captures a bit more of an extensive complex here, but does appear to miss some areas. And this is likely due to the difficulty in kind of NHD and DMs of mapping stream channels that have are multi-thread systems well. And so it may be that this is not quite picking up the full connectivity of the system as actually occurring on the landscape. And finally, here we have the National Wetland Inventory map, and that shows the largest extent is being mapped here. It looks pretty good compared to the imagery. It's showing a mix of emergent wetlands, forested shrub wetlands, lakes, ponds, and it probably does the best job here if your goal is to extract data across the full complex. But it does also include that area that may be agricultural, so that's something you'd have to pay attention to if you're using this data set. For our second example, we're moving to quite a different context here in southwestern Colorado along Yellow Jacket Canyon, where there's a relatively narrow riparian corridor. And here you can see that NLCD captures a kind of a thin strip here of woody wetland along the vegetated main stem. VBET captures something similar, but slightly more extensive, and does seem to include some areas that are adjacent to the river that probably are shrubland systems as well. And also does include the tributaries that may be ephemeral coming into the system. NWI, despite a recent update, does not map this area as riparian wetland, and so provides limited utility for defining an extent. So these are just two examples. They highlight that anywhere you apply these extents, you'll need to look at whether the mapping products fit your needs. These products can provide incredibly useful ways to scale masking out to areas of interest, but you do have to think about the implications and the quality wherever you're applying them. Next, I want to talk briefly about applying data sets related to climate and drought observations using GridMet and GridMet Drought. I know these data sets were covered back in the Climate Engine Basics training, so I just want to really focus on a few considerations for riparian and wetland applications here. Most importantly, when you're working with riparian and wetland questions, we're usually interested in aggregating climate and drought metrics over time. So you want, as you use these products, you might want to be thinking about aggregating them to a water year or a season or perhaps a month. You also might want to be using, rather than using a raw metric, be using a standardized drought index. And you can calculate those on the fly using GridMet, or you can use a pre-computed data set, which is GridMet Drought, to pull up these standardized indices. A particular use is SPEI, which describes both drought as accounting for both precip and reference ET. And again, kind of as you look at what metric you want to use and the time scale, you'll probably be wanting to think about using something somewhat longer timescales in a lot of cases. We often use timescales when we're thinking about drought in these systems of somewhere between 9 months and a year, because that's better able to capture the dynamics of hydrologic drought, which can be really important for describing dynamics within these systems. Next, I want to get into talking a bit about vegetation and water data sets, of which we have multiple different options in Climate Engine. One thing about analyzing riparian wetland systems that's somewhat distinct is that we lack a lot of derived products that are useful. And so mostly we rely on the spectral indices that come out of our remote sensing satellite imagery. And within Climate Engine, we have a number of different, several different imagery sources, from Landsat to Sentinel-2 to a harmonized version of both of those, and also NAPE. And then there are a number of different spectral indices that you can use to choose from. We're going to focus mostly on NDVI and NDWI, but know that there are many more that can be used. And there are also a handful of derived products that can be somewhat useful, including OpenET, which provides monthly evapotranspiration estimates, and the MESIC Resource Restoration and Monitoring Aid dataset, which provides a classified product mapping uplands, mesoclimatic vegetation, and water. So let's talk a little bit more about the spectral indices that we'll use in these systems. And generally we can divide these into indices of greenness and wetness. Greenness indices, such as NDVI, attempt to measure photosynthetic activity and are often used as a proxy for vigor or productivity. Wetness indices attempt to measure the presence of moisture. There are two flavors of these. Some focus on moisture content in vegetation and soils, and others focus on the presence of surface water. Unfortunately, both of those flavors are often called NDWI as an abbreviation, so you need to pay attention to what you're actually using when you use those indices. It's important to know too, that when you use NDVI in these systems, surface water generates low NDVI values. And so you can see that here in this example where we see, a stream channel with a riparian zone that's green and has high NDVI values. The channel itself has low values, and that's because the water itself will come out with low values. Conversely, if you look at NDWI for water, you can see that the areas with surface water pop out as having high values. So using both of them together can be really helpful. We're going to see that again in a moment. So I want to talk a bit about how we apply remote sensing in riparian wetland systems. And so we have quite a bit of opportunities for how to apply these. We can apply these to summarizing values, anomalies, trends, and time series. And later in the training, we'll show you how to do this. But with these opportunities, we also want to reflect a little bit about how do we maximize opportunity and how do we avoid common pitfalls. So first, it's important to know that vegetation indices, spatial indices can be really effective for tracking phenology, productivity, and vigor. But there's also that potential for confounding signals from water presence in soils. Also, when you're using NDVI as a proxy for vigor and sometimes condition, it doesn't always tell us what vegetation is on the ground. So it may not speak well to certain concerns like the presence of native versus non-native species. Second, it's important to know that the timing of the phenology in these systems is quite different from upland systems, and they can be really dynamic year to year as well and between years. And so you're always going to be thinking about what's the temporal aggregation period. What's the best period to be aggregating over as you look at as you try to calculate values over these images. And typically we focus our analysis on summer or late summer, as these periods tend to best reflect peak phenology, and they also avoid some of the confounding issues that can happen with the presence of snow or spring flooding or other factors. Third, you'll want to be thinking about the spatial and temporal trade-offs in these data sets. Riparian systems can be small and they can be highly spatially variable. So finer resolution data sets like NAPE or Sentinel might provide more information that's useful than Landsat, but Landsat has a record going back to 1984, while Sentinel-2 has a data set going back only 2017, and NAPE is only collected every 2 to 3 years. So for longer-term analyses, even though it's coarser, using Landsat may still be the way to go. And finally, we want to caution you all to not assume that data sets that are derived and generated for upland systems can be applied in riparian wetland systems. In our work, we found that data sets like RAP and RCMAP that provide fractional cover and production data are incredibly helpful in uplands, but perform quite poorly in riparian wetland areas. So to kind of reinforce some of these ideas, I'm going to give a quick example here that also previews some of the analysis that we'll do in our case studies. So here we're looking at long-term trends in August NDVI along Maggie Creek in Idaho. And mostly we're seeing increasing NDVI trends over our 40-year record. But we do see this anomalous looking decline right here in the southern portion of the map. And so if we look a little bit closer at the imagery, we can see that this creek is part of there's a large beaver meadow complex as part of the system. And kind of where we're looking is right around where there's some beaver ponds and channels and quite complex topography and vegetation and open water. If we pop open time series here, we can see that there's this really clear trend towards higher NDVI values, kind of pre-2000, a drop in NDVI, but then an increase in the last couple of years. And so what we might do first is think about, well, is climate driving these patterns? And so we might build this relationship between 1 year SPI, how droughty is the conditions in a given year, compare that to this NDVI value. And we do see some relationship here, but it's not that strong. It doesn't really explain the variability that we're seeing in the time series. So next we might think about, well, what else can we pull from Climate Engine to help us with this? And one thing that could be really helpful, because a lot of this is happening in the recent period, is looking at NAPE imagery, which we have going back to 2003. And one of the key things we see in this NAPE imagery is that there is this beaver pond, and that beaver pond seems to be expanding and contracting through time. And so we see, in 2003, it looks relatively small. Look at 2011, it's bigger. 2013, it's bigger. In 2017, it seems to hit a maximum extent. There was a large fire that came through the system in 2018. It didn't affect the riparian area that much, but you do see a contraction in the beaver pond by 2019. And so that starts giving us some ideas of, okay, what might be happening here, explaining this pattern. Is it, is this decline that we saw a reflection of negative conditions? Potentially not. More likely, it's just simply describing the dynamics of an expansion and contraction of a beaver pond that's happening within the system. And again, if we look again at that trend NDVI, we see that strongly negative value. But when we go look at the NDWI trend, it's the inverse. And so we can actually kind of see that at least part of what we're seeing here in the system is just kind of this interplay between surface water and vegetation and how that affects our indices. And that can be really useful to identify, so that we're not kind of zooming in on this area as an area of decline. Instead, we're just understanding that it's describing this dynamic of this complex system. So with that, I'm going to hand it back over. I think I might have a couple minutes for questions before we get into our next conversation with Wyatt Fereday.
Hey, thanks a lot, Alex and Eric. We appreciate that. Really nice example there, showing just how dynamic riparian areas are and what satellites can and can't see. Alex also did a really nice job of talking about the trade-offs of spatial resolution, temporal resolution, spectral resolution, and it seems these are often amplified in the riparian world. Okay, so I'm going to take a quick pause here right now. This concludes our 20,000 foot view section of the training today. So now we're about to step down into some local examples. But again, before we do that, just wanted to take a quick pause. If there are any questions, feel free to chime in, or as people have been doing, please do so in the chat as well. Give it just a minute here. I suspect this might not be the case at the second check-in with questions, because after the next presentation, we're going to have a couple of different demos, 3 different demos before we close things out. Okay, well, what I'd like to do now is we're going to step down into some local examples, and I'm very excited that Wyatt Fereday has agreed to join us today and talk a little bit about how he has addressed some ecological questions in the Carson City District Office. And Wyatt's a hydrologist in the, well, actually, Wyatt, I don't know if you're in the district office or the Stillwater field office, but I know you hang out in both of those areas. But nonetheless, I'm happy to turn it over to Wyatt. Wyatt's going to give us some insight into how he's used some of this data to answer questions in his neck of the woods. So with that, Wyatt, take it away.
All right, thank you, Tim. Yeah, as they said, my name is Wyatt Fereday. I'm a hydrologist in the BLM Stillwater Field Office and the Carson City District Office. And I'm going to go ahead and share my screen for my presentation. Can everyone see that?
Yeah, we can see it, Wyatt. Thanks.
Great, awesome. So today I'm just going to present 3 quick examples of how I've used remote sensing in Nevada. These aren't all in the Carson City District. They're just in the state. And my 2 main data sources are the Climate Engine app for remote sensing data and the Nevada Division of Water Resources Water Levels Dashboard, not a remote sensing product. But I wanted to look at the relationship between them and make some correlations. And then I was really curious about how we could use this remote sensing data to look at monitoring and how resource conditions change due to land management decisions. So my first example is at Abraham Spring in the Carson City District. In 2012, a riparian exclosure fence was installed because, as you can see in these photos, it was pretty beat by cattle. It's basically no riparian growth in this area. It was completely trampled. And so here I decided to track the NDVI over time. This is the same spring photo from 2019. You can see the pipe rail fence that was upgraded. It's been effective. Obviously, the pictures kind of are worth 1,000 words. But what does that look like in terms of the NDVI data? And so here in the yellow to green line chart is our June, July, August mean NDVI for this riparian area. And you can see when in 2012, when the exclosure fence was installed, we immediately get a drastic increase in the NDVI signal. And what's really cool is, well, we know that, you know, the spring was visited maybe once or twice over this time period, but the NDVI gives us this data set back to 1985. Here I've only clipped it to 2000 just for effect. The bar graphs shown in red and blue are precipitation. So you can see even at a similar range in precipitation, the NDVI is higher post-exclosure fence construction. This is showing the same thing as the time series chart I just presented, except it's a regression plotting NDVI as a function of precipitation. And here you can see that there's consistently a higher NDVI value shown in the blue data set, breaking the data set between the post-exclosure fence construction and the pre-exclosure fence construction. There's a consistently higher NDVI signal over basically the same precipitation range as compared to the pre-exclosure fence. It's not earth-shattering, it's sort of obvious, but it's really good to see that the data clearly reflects what we're seeing on the ground and illustrates that NDVI can be a great analog for riparian vigor and riparian health and track these changes over time. And you can also note that the trend line for the post-exclosure period falls outside the 95% prediction interval for the pre-construction period. Okay, so my second example, this is not in the Carson City District. This is down northwest of Las Vegas in Amargosa Desert. The Ash Meadows riparian area is this large riparian area here. It's federal land, not BLM. It's U.S. Fish and Wildlife Service land at a National Wildlife Refuge. And the riparian area I'm concerned about that popped up was when I pulled the Climate Engine NDVI trend map from 1985 to 2023 or 2024, I think. It shows here that this spot popped out bright red. So that's shown a big decrease in NDVI signal over that time period. I said, well, okay, well, look, this is only 5 miles west of a bunch of agricultural wells here that irrigate these pivots at a dairy. Over here on the left side, we have the Nevada Division of Water Resources groundwater levels dashboard. You can see a massive decline in this hydrograph shown at this agricultural well here. We're down about 80 feet over the span of about 40 years, which is 2 feet per year, a pretty drastic decline. So are these linked? Let's find out. So I pulled over that polygon on the riparian area. We see the NDVI decreasing here on the bottom chart, and then basically flattening out at a very low value, essentially dewatered or no longer riparian. And then that trend from 1985 to 2023, that slope really matches with the groundwater level decline as well. So I just really like that example. There wasn't a particular land management decision here at play. Those pivots are on private land, but I just found that it seems that in this area you can see effects where this riparian area is truly affected by a declining, or potentially affected by a declining groundwater level, as indicated by this correlation. I want to be clear that I'm not saying anything as a causation in this example, because this is not an official study. This is just me playing around with Climate Engine and showing some of the cool things you can do. These springs up at Ash Meadows are large carbonate aquifer regionally sourced springs that are extremely consistent in their discharge. They are not very sensitive to climatic variation, droughts, wet years. They kind of do their thing each year. So to see a drop off like that means that further down in their outflow zone in this area to the south of those spring heads, there's something going on. And that appears to be dropping groundwater levels. So here again, as I was saying, in red, in the pre-water level decline era, we have NDVI values within that riparian area that are essentially not sensitive to precipitation, which is common in these large carbonate springs that are extremely non-sensitive to wet and dry cycles. But then in the post groundwater level decline, we see in that riparian zone, we are not only drastically lower in our NDVI values, but we have a slight correlation, very slight correlation with precipitation. And finally, my third example, this is back in the Carson City District and does have a land management decision at play. We're going to look at the Patchogue geothermal plant and its potential effect on the Patchogue hot springs. Again, I'm only looking at correlations here. I'm trying to not make any conclusions on cause and effect, but Climate Engine is a good place to start to find these correlations. So here at the Patchogue Hot Springs complex, we have dozens of springs, maybe a few more. They're all quite hot. These red dots are the Patchogue geothermal wells. The Patchogue wells for the plant, which is just off screen over here, these wells are all on private land and Bureau of Reclamation land. The hot springs are on BLM land and they're adjacent to the Fernley Wildlife Management Area. The Patchogue geothermal plant was authorized by the Bureau of Land Management because we issue decisions for fluid minerals on federal land. So what was really interesting here after visiting the hot spring was I was curious, well, do we have any data on it? And I finally found actually from NDWR, they have spring flow data. And it just so happens that it started at the same time, 2013, that the geothermal plant went into production. And we have a very obvious decline from 3 gallons per minute down to less than a gallon per minute discharge at the one spring that was monitored. Unfortunately, DWR doesn't have any data beyond 2023, and they don't have any baseline data prior to 2013. So my question here was, well, how do I say what the hot spring was flowing before geothermal production, and how can we tell whether geothermal production was affecting it if we don't have data before the production began? So that's where the Climate Engine really can pack a punch. In this lower chart here, I pulled this data from the Nevada Division of Minerals, and it's just showing the geothermal pumping began in 2013 and has stayed steady. I wanted to rule out other factors, so I looked at a nearby monitoring well, the closest monitoring well I could find. Groundwater levels were steady. That doesn't explain the declines in the Patchogue hot spring discharge. So first, I went into Climate Engine, selected this polygon on the Patchogue hot spring complex, and just looked and plotted that data as a regression compared to the spring discharge from DWR. And it turns out we get a really nice correlation between decreasing NDVI with decreasing spring discharge. So clearly the riparian intensity or riparian health is correlated with how much those springs are flowing. Now, going further back in time, looking at the June, July, August NDVI, we can separate out the pre-pumping, pre-geothermal pumping time period in blue and the post-geothermal pumping time period in orange, and plot those on the time series chart, comparing it with precipitation. And while precipitation stays steady, even increases slightly on average over time, we see a clear declining trend in NDVI after the start of geothermal pumping in 2023. Data, but just plotted as a regression, comparing June, July, August NDVI with precipitation. We see, as with Ash Meadows, those large regional springs, these hot springs tended to be relatively consistent, or the riparian area resulting from the hot springs was consistent pre-pumping, and now it tends to be not only lower, but more linked with precipitation post-geothermal production. So in summary, I found remote sensing tools to be extremely useful in evaluating the effect of land management decisions. And the reason being is that we can easily track trends with a consistent, unbiased approach. and get long-term data sets back to 1985 for Landsat and NDVI in particular. Easy to compare NDVI or other variables with precipitation. And we can quickly produce trends, charts, export that data to Excel, and just play around with it. And so I hope to continue to use these tools, particularly at this is the picture of one of the Patchwell hot springs that me and my fellow hydrologist here in Carson City District went out to investigate. So we're looking forward to using these tools to continue evaluating the effectiveness or result of land management decisions here at the BLM in Carson City. Thanks. And if anyone has any questions, I think we have a couple minutes.
Yeah, I think we should pause for a couple of minutes and see if there are questions for Wyatt. Yeah, thank you very much for that presentation, Wyatt. That was really helpful. And yeah, Wyatt, you attended a climate engine training probably 2 years ago at least. And it's really cool to see how you're actually applying some of these tools in a bunch of different contexts, and seems like I'm always discovering new things that you're doing. So yeah, questions from the audience. And if there aren't any coming to mind, feel free to add them to either the Q&A in the chat. We can always circle back as there are questions and come back to them later.
I guess I'll just say thanks for Eric, Tim, and Alex, and all the DRI folks for giving me this opportunity.
Yeah, and thank you, Mark, for pointing that out. So Wyatt's slides are separate, so we will be making those available along with the recording after this. Wyatt, if you have a link, feel free to throw them in the chat. I know sharing is sometimes a little bit difficult, so we'll find a way to get those packaged up and shared with everyone, as long as you're comfortable with that.
Yeah, absolutely. I can send this the PDF. I can drop it into the chat if that'll work. If not, I can email it to you, Eric.
Yeah, sounds good. If you're comfortable with that, why don't you do that, and then we'll do all of the above. We'll get them from you afterwards as well.
Perfect. Sounds good.
So the rest of our session is going to be focused on hands-on demonstrations in the web app. And our first demo is going to be focused on Maggie Creek in Nevada. This is a large basin that's received a lot of riparian restoration in recent decades. And so it's a really good example for looking at effects of restoration using satellite data. It's quite a large system with a wide valley bottom, and so it's a good example for us to focus on. And this demo is really going to be focused on mapping this system. And so we're not going to be pulling any time series. It'll be entirely exploring the types of maps that we can make in Climate Engine. So Maggie Creek is an example that's gotten a lot of attention in recent decades, and that's for good reason. Prior to the early 90s, there was very extensive livestock grazing across this system, and that began to have very serious impacts on the vegetation and the hydrology of the system, leading to severe erosion across the system that led to kind of an inflection point where grazing modifications and restoration actions were applied. So that period began in the late 1990s through the early 2000s. And over the course of this project, beavers began to move in the mid 2000s and really expanded during that period. And there have been substantial improvements to both the habitat quality in the riparian zone as well as the hydrology, as they've been able to reverse some of the erosion effects that had occurred in this system, and more sediment deposition has been able to occur as the beavers have had a more profound impact on the system. And so this is the example that we're going to begin with here. And like I said, we're going to be creating a number of different maps associated with this system. And so for all of the maps that we're going to create, you'll be able to use these links to open them up in a new tab and explore these data on your own. But I'm going to walk through how to create these maps in the web app as well. Okay, so I'm going to move over to the Climate Engine app here. And to get oriented, we're going to zoom in on Maggie Creek. So we're going to be in this zone right here, kind of, you can see almost due west of Elko, Nevada, so kind of north central Nevada. And before we jump into producing some of these maps, I want to walk through some of the new features that we've added that we talked about earlier in this session. So a couple places where things have changed. The first is this menu above the main map window. So these had different options prior to these changes we made. You'll notice that now these reflect some of the updates that we made. So if you click the base maps option, you'll see that that's where all of the NAPE imagery, all of the historical imagery, we now have topographic maps, we have the high resolution digital elevation model data sets. If you click this question mark, that'll open up a page with more information about that data source. So that's where all of these layers live. We moved these computed map options. There used to be an option for colors that modify the colors of your maps that we might use in this session at one point. So that lives here in this computed map section. And then for the map overlays, these are the raster data overlays that we can apply as kind of contextual layers. So for example, if I turn on the Surface Management Agency layer, then we'll see that actually this system is primarily private land. And that's pretty common across Nevada, where a lot of these kind of larger valley bottoms that have more agricultural value and opportunity are largely private. And so with this work that we're highlighting today, BLM was a partner to a lot of this work, although a lot of the work actually was applied on private lands. So that's one contextual layer. We also have the Valley Bottom Extraction tool, which we'll be looking at quite a bit more here. And you can see how that looks in this area. And then we have the National Wetland Inventory here as well. Okay, I'm going to turn off these layers for now. I do want to show the base maps here really quickly. So if we turn on the historical imagery, we can get a good picture of what this system looked like back in the mid-1950s. And we can see that back then there was still human modification on these systems, and that this has probably been used agriculturally for quite a long time. And that a lot of these boundaries that we still see on the landscape existed back then to some extent. All right, I'm going to turn off this layer now, but just know that that's where all of the high resolution imagery is, and we'll look at that a bit more throughout this demo. So I want to create a map of this system. And the first thing that I'm going to do is just create an NDVI map for the last 3 years during the summer period. So we're going to be using remote sensing data. So for the data type, I'm going to select remote sensing. And then we're going to use Landsat NDVI. So we can keep this data set and variable exactly the same as it is right now. Now, what we're going to do differently is I want to create an average NDVI map over the last 3 years. And that'll, things can vary from year to year, so that gives us a good picture of kind of this system in general. So to do that, I'm going to select average conditions. And then I'm going to define my period of interest as July 15th through September 30th. And that's a good range for capturing this, kind of the most water limited part of the year. And so becomes a good indication of how much groundwater or surface water is there available for this system, because most of the, soil moisture and moisture that fell, earlier in the year is not going to be influencing this vegetation. And then we're going to create an NDVI map for the last 3 years, from 2023 to 2025. And we'll see that map come back. And we can see on the landscape the most productive areas here where NDVI is the strongest. Another layer that we can highlight here is the 3-dep layer. So this is a 1 meter digital elevation model. And so here we can see that this appears to be where the main channel is flowing through this system. So this can be, the Landsat data itself is somewhat coarse. This 1 meter data, we can get quite a bit more detail with regard to the kind of surface topography and hydrology of this system. So here's the hillshade overlaid, on this system as well, and we can see the most productive areas kind of in that most kind of where the main channel is located. All right, I'll turn that off for now. So now what I want to do is show you how we can create this map just for the valley bottoms. So I showed the valley bottom extraction tool. I'll turn that back on. So here's where our valley bottoms are. Now we can create a map of NDVI over just the valley bottoms by using this masking option. So we have this new mask by category option here. And by default, the valley bottom extraction tool will be selected. And you'll see that there are 3 options: non-valley bottom, elevated valley bottom, and low-lying valley bottom. So in the green and the blue, you can see the low-lying valley bottom and the elevated valley bottom. So I'm going to select both of those options. If you're interested in just seeing the low-lying valley bottom NDVI values, you could just select that. So now when I click Compute Map, I will get a map back that if I turn off the VBET layer, it's just NDVI values over this valley bottom, over the valley bottom areas. So this becomes, a really powerful way to focus attention on, at this network scale on the valley bottoms from VBET. We can produce all the same types of maps that we're used to in Climate Engine in this way. So if I select a slope of trend map, and I want to map trends in NDVI over 30 years from 1996 to 2025. That same mask option is going to be turned on. And now we can really see the effect of that restoration work that was applied. And we can see these really deep blue areas where vegetation is really much more productive in some of these areas. So if we zoom in on one of these areas, this is where you can also use this high resolution imagery. So if I turn on the NAPE True Color, and it'll tell you what years are available. So the earliest year is 2006. And I have to make sure I turn it on. So there you can see 2006 imagery. And I think the most recent year is 2022. And so we can see much more kind of woody vegetation that seems to have come in. And so that may be a significant part of why we're seeing these really strong trends in NDVI over some of these areas, is perhaps an increase in woody vegetation. You can also apply the same confidence mask to these areas. So if I want to filter at a 0.05 p-value, we can show just the 95% confidence trends over the valley bottom extraction tool areas. So that all works correctly. The last thing you can do that I'll highlight here is you can actually layer masks on top of each other. So, in this case, and I'll turn off this p-value mask for now, just so things are a little bit more clear. But for example, if I turn on the National Wetland Inventory layer, we'll see that there are some NWI areas that fall outside of the valley bottom, which makes sense. These might be kind of these emergent spring-fed systems. There are going to be some differences. And if you're interested in kind of all of the riparian wetland systems across an area, you may want to use both the VBET and the National Wetland Inventory areas. So if that's the case, you can actually apply a second mask. And here I'm going to select areas to do the union of the National Wetland Inventory and the VBET. And I'm going to turn on, we'll just turn on all of the NWI areas. So now when I click Compute Map, I'll get a map that shows NDVI trends over the combined area of VBET and the National Wetland Inventory. And so now you can see that all of those National Wetland Inventory areas are now covered by the map that we get back. And so if we zoom in on this particular area, some of these areas were not covered before. Got a lot of layers loading in here. I'm going to turn off this true color imagery because we're not using that actually. So now we can see that all of those areas with the combined VBET and NWI are loading into our map. So that's the extent of this demonstration. It was really to show you how you can use these masks to perform some of this network scale mapping, and hopefully to be able to really focus the analysis that you're doing in Climate Engine on these riparian areas. All right, so our second demo is going to build on our first one. So in the first demo, we really focused on mapping riparian and wetland systems in Maggie Creek in Nevada. Here we're going to be doing more site-specific analysis. So we're going to be looking at groundwater-dependent ecosystems, spring-fed ecosystems in Diamond Valley, Nevada that are on BLM land that have been impacted by groundwater pumping for agricultural use in this area. So Diamond Valley is a significant agricultural valley in central Nevada. Historically, it's a large groundwater discharge zone supporting more than 200 seeps and springs, more than 5,000 acres of mesic meadow, and endemic aquatic species. It's also been critical habitat for greater sage grouse for brood rearing, and it's become an area where adjudication conflicts have occurred related to federally reserved water rights that BLM has worked to demonstrate. So a little bit of history. Agriculture really started to pick up in this region in the 1960s and 1970s. Heading into the 1980s, hydrographs started to strongly record some of the declines in groundwater in this area. That resulted in Thompson Spring ceasing to flow in 1990 and an extirpation event impacting aquatic invertebrates. And this basin then was designated a critical management area by the state of Nevada because of the groundwater pumping and the types of impacts that were observed. So looking at these maps, these are from a USGS report. We can see a couple of things. So in this first map, we can see kind of flow lines for groundwater flow flowing from higher elevations in the southern part of the valley to the lower elevation playas in the northern part of the valley. So we'll definitely see that as we investigate this in Climate Engine. The other thing that we'll see is significant declines in groundwater levels. And this report, I believe, was from 2006. And so the results are only up through 2006, but we can see major declines at many of these wells in the southern portion of the basin in particular, and then to some extent further north as well. And if we look at the hydrographs for these 3 sites in Diamond Valley, we can see the precipitous declines in groundwater across these areas. So BLM back in 2015 tried to use public water reserves as a way to protect these springs from agricultural dewatering. And this effort was partially successful, but most of the public water reserves that were claimed by BLM were not supported by the state engineer. So the BLM filed 66 claims and 27 were validated. And some of the reasons that some of these claims were invalidated were because by the time field crews went out to demonstrate these water reserves, they were so degraded that they were functioning only as seeps, and it became difficult to demonstrate that these were functioning systems at one point. And so the ruling was effectively that because the springs are dry now, the government has no right to that water that used to be there. And so this is an area where remote sensing could be quite useful, right? Remote sensing data, like we talked about, go back to the mid-1980s. And so while they don't go back as far as we may want to characterize the types of impacts that might go back to the 60s or even before that, they do give us a nice record over the past 40 years of how things have changed. And so that's what we're going to look at in Climate Engine. The rest of these slides in this section, I'm going to go through in the app, but I do just want to mention that each of these maps that we're going to go through again has links in the slides that you can go through at your own pace. And I don't think I'll quite get to this last example, so I'll mention that at the end because it'll build on some of the things that we do throughout this demo prior to that. Okay. So I am going to go over to the Climate Engine app, and we will zoom in on Diamond Valley in kind of central eastern Nevada. So you can see we're just north of Eureka here, and we can very much see that pattern where the agricultural kind of center pivot areas are in the south, and the north is extensive playa system. So I want to orient to this region just a little bit as we get started. One thing that's interesting to look at is if we turn on the historical imagery, which in this case is from 1954, we can see that there was very little agricultural activity, just a few fields across this area. So we can really see the expansion in agricultural activity there. Another thing that we can look at is the land ownership matrix across this area. So we'll see that here, and I'm going to turn off the historical imagery. We'll see that the center pivots are largely private. Some of these other significant wetland systems are also private, but much of the land here is BLM land. So BLM is a major manager of a lot of this land. The other thing I'll highlight is the extent of the National Wetland Inventory. So in the blue, we can see the lakes in this area. So that's going to be a playa. These are going to be less kind of productive wetland systems, but we can see kind of dotting the edge of this area. We can see a lot of mapped freshwater emergent wetlands, herbaceous wetlands across this area, and some in the deeper green here, woody wetlands as well. So that's what we're going to be focusing on here. So I want to characterize some of the decline in this area while we get started here. So the first thing I'm going to do is create a trend map in NDVI, much like we did in the last demo. So here I'm going to again select remote sensing, And as you'll remember from last time, Landsat NDVI is selected by default. So we're going to create the same map as before. So I'm going to select slope of trend as the calculation type. And I'm going to select the same day range. So July 15th through September 30th. And we'll again, here I'm going to select the entire period of record from 1985 on. 1984 was the year that the first Landsat satellite and kind of the modern archive was launched. And so you do get some, a lot of people like to exclude that year. Calibration was happening with those data. There were definitely some things to be sorted out. And so here we're seeing really clearly some of the changes that have occurred in this area. So we can especially see in a lot of these wetland areas, this privately owned large complex on the west, and then at the toe slope of Diamond Peak and this mountain range on the east. And really in a lot of these areas that are mapped as wetlands, we see declining NDVI. So if I zoom in on this particular system, we'll see if this wants to load at a little bit higher resolution. I'm going to just click compute map again, and that'll force it to rerun. And then we'll get our map back, hopefully. It is running. It's worth appreciating that, you know, this is pulling every Landsat image in this area for the last 40 years over this period. So there is a lot happening here on the fly. So with these types of calculations in particular, you know, you may see that things take a little bit of time. I think if I shorten this time period a little bit, things might run a little bit faster. So now I get a map back. This is just for the last 25 years, but we can see that decline has really occurred in this area. So we're going to investigate this system a bit more. And the first thing that I want to do is just visually inspect it using high-resolution satellite imagery, or sorry, high-resolution, in this case, aerial imagery that was collected by airplanes. So I'm going to turn off this layer where we can see it looks like it's showing, you know, declines really in kind of the southern and western portions of this unit. So we're going to use the high resolution NAPE imagery, and I'm going to select 2006, which is the first year of imagery available for this area. We'll turn that on, and we can already see that this system was much larger back in 2006. If we jump ahead to 2013, we can see in that year it had contracted quite a bit. 2017, and then 2022. So you can see this system's been getting quite a bit smaller. You want to be careful, you know, interpreting too much from the NAPE imagery. The NAPE imagery can be collected at different times of the year. You know, it's going to vary in a few different ways from year to year. And so we want to be a little bit careful drawing too many conclusions, but we can certainly see that this system has contracted in a way that is consistent with what we're seeing in this map here. So what we can do to take this a bit further and make it a bit more quantitative, start to pull some more data for this area, is start to make some time series graphs for this area. So to do that, I'm going to select the Make Graph tab, and I'm going to turn off a couple layers here. I'm actually going to turn off our computed layer as well. I'll keep that on, that's fine. But here we're really going to use the National Wetland Inventory data. So what I want to do is create a time series plot of, for each year, the late summer NDVI for this wetland system here. And I'm going to show you how to do that. To do that, we're going to select the summary time series option. And this will allow us to calculate an average over some period we're interested in each year over the period of record. So that's enough for us to get started. And then I'm going to draw a polygon around this system. And in this case, I actually don't need to be very precise at all. And that's because we're going to use the same type of masking that I showed you in Maggie Creek. So I'll show you that in just a minute. For right now, we're just fine with this menu here. We're going to select Landsat and DVI. That's already selected, so we're good to go. And here's where I'm going to apply this mask. So here I'm going to select, again, mask data by category. And now I'm going to turn on the National Wetland Inventory as our layer. And here you'll notice that there are a couple wetland classes that my polygon is intersecting. And I'm only interested in this green polygon. This blue area is considered lake bottom. So you can look at this legend to help you interpret what classes these are. And we can see that this is freshwater emergent wetland here in the bright green. So I'm just going to select that class. And my form otherwise is already set up the way I want to. I want to pull NDVI over the late summer period from 1985 to 2025 over this area. And so here we can really see that this decline started around the late 2000s. And we really see that decline kicking in over the past 15 years or so. So this is already, telling a pretty compelling story. Now, to take this a step further, we can account for the role of precipitation in climate. And that's really important because in a lot of areas of the West, we are seeing declining precipitation. We are seeing just a less favorable kind of hydrologic environment. And so we want to be able to account for potential impacts from climate. And that's something we can do quite, straightforwardly in Climate Engine. So I'm going to show you how to do that. Here, we're going to switch to a 2-variable analysis. And so I'm going to select GridMet precipitation as my first variable. And that's because you always want your response variable, in this case, NDVI, the vegetation, to be variable 2. And you want, whatever the environmental driver is to be variable 1. So that's going to be precipitation. So here we're going to use GridMet as the precipitation data set. Alex talked about GridMet a little bit earlier. And for GridMet, we want to summarize precipitation over the entire year. So we're going to use the water year, which starts on October 1st and ends September 30th. And then for our second variable, we'll just switch that to Landsat NDVI. And we're going to use the same period as we used before, July 15th to September 30th. And we need to remember to apply the same mask as we were before. So I'm going to select National Wetland Inventory and Freshwater Emergent Wetland. And now both of our forms match and we can pull our time series data. And so now we're going to be able to see, okay, we see this declining vegetation. Are we seeing, is there declining precipitation per year that corresponds with these types of changes? And what we see is, now the vegetation is this line plot, and we can see the declining vegetation. But precipitation's kind of all over the board. There's some above average years, some below average years. There's not any real obvious trend in this area. So that's a pretty strong clue, but we can make this just a little bit more quantitative and really demonstrate, while accounting for precipitation, how much productivity we are seeing in this system. So to do that, we're going to modify our plot from a summary time series to a 2-variable scatter plot. And so what that's going to do is put precipitation on the x-axis, NDVI on the y-axis. And what we can do is actually separate out the pre-restoration period the pre-impact period from the post-impact period. So if we think it was about 2009 where things started to shift, I'm going to define 1984 to 2009 as our pre-impact period and 2010 onward as our post-impact period. And so what this is going to do is plot each of these two periods as just separate colors and separate colors and shapes. And so I am going to turn on all of these options for our statistic. And what we see here is, there is some overlap here. Some areas where we look at this relationship, it's a little bit cleaner. You really see some separation between that pre and post impact period. But what we can see here is that in the red triangles, the pre-impact period, while accounting for precipitation, NDVI was just much higher. And then once the system started to be impacted, we have much lower NDVI while accounting for precipitation. And so this kind of outline here, like Wyatt showed earlier, is showing that pre-period 95% prediction interval. So it's pretty statistically meaningful that so many of these years are falling outside of that, below that 95% prediction interval. So this becomes a pretty powerful figure to be able to include in a report or in perhaps an adjudication filing in this case. So that is the end of this demo. I'm going to go back to our slides here and just highlight. So you'll see all of the links are included here for producing these figures. I did run this example for a larger area over basically the entire northern basin. And what we start to see is that even at that kind of basin-wide extent, we are seeing statistically meaningful declines. So you can look at those same figures as I just demonstrated for that local system over this whole area, over all of the freshwater, emergent, and forested wetlands. And so, this is a little bit more novel. I think to really make this meaningful, you'd want to know a bit more, frankly, than I do about the hydrology of this area and whether, in fact, this system is all connected in terms of the groundwater hydrology. But I think it's pretty, to me, it's pretty interesting that we can actually see these impacts at this really coarse type of scale. And that could be pretty meaningful for describing a basin-wide type of decline. And remote sensing is really positioned to help you to do that. The last thing I'll highlight here is that this workflow with these scatter plots that I showed and being able to overlay the 95% prediction interval, that's all published. So we actually have a tutorial video walking through that methodology in a bit more detail, or you can look at that publication. The publication is focused on demonstrating outcomes of riparian restoration. And so it's a little bit, kind of the flip side of what we're demonstrating here. We're trying to demonstrate degradation of these systems here, but it's worth looking at and worth understanding both some of the opportunities to use this as well as, some of the areas, some of the types of cases where you want to be maybe a little bit cautious. So strongly encourage you to take a look at that publication if you're interested in it. It's quite readable, I think, and a good one to look at. And so with that, we're going to transition to over to Alex, and Alex is going to walk us through a bit more of a kind of capstone type demo here, characterizing riparian restoration effectiveness and pulling together quite a few of the different pieces, bringing in some field aim data as well. So I hope this will be interesting for you. Thanks.
So we're now going to look at a case study from Rowland Springs in Northwest Nevada. This demo builds on what we just learned from Eric's demonstrations and attempts to show how we can start to think about how to fit climate engine analysis into broader workflows. We'll focus on a site where Climate Engine can support and complement field measurements from BLM's Assessment, Inventory, and Monitoring Program, also known as AIM. And this demo is a spin-off from ongoing work that we have at DRI, working with BLM to develop better guidance on integrating remote sensing with field measures for BLM assessment and planning. Rowland Springs is a site we're going to look at today. It's a great example of a site with multiple layers of disturbance and management interventions. It's a small system, but provides important habitat for many species, including pronghorn antelope, mule deer, antelope, and greater sage grouse. Livestock also graze here, including sheep and cattle, and wild horses, and they rely on this area for forage and use the spring for water. It also has important cultural resources, which has motivated some of BLM's recent efforts. BLM acquired the parcel sometime between 2010 and 2012, and the area was then hit by a large wildfire, the Rush Wildland Fire, in August 2012. In 2015, a small fence exclosure was installed around the spring head, but it was found that it resulted in increased impacts to cultural resources around the spring, and so more work was needed. Subsequently, in 2022, NEPA was completed for a riparian restoration project, which led to multiple recent improvements, including a large fence exclosure, which was installed in 2023. Improvements were also made to the road and creek crossing, and dead standing junipers were removed that were burned in the fire, and then 4 ZDX structures were also installed with plans for more, with willows also planted in the drainage. We look a little bit at some photos of the springhead through the years. We can see that things are in pretty rough shape in fall of 2022 after the fire, without much vegetation present. By 2016, we can see the exclosure on the springhead here on the right-hand side, and we see there's a lot more vegetation and less bare ground. But if we look downstream past this pond here, we can see there's still, that there's not much vegetation in the drainage way going downstream. If we jump ahead to 2022, we can see more vegetation in the exclosure, but again, it still looks pretty impacted downstream. In 2024, we can now see down below that the new fence has been installed that extends past the original fencing, and we can also see an example here of a ZDX structure. So from an aerial view, here's the site with the 2015 fence in green and the 2023 fence here in purple. You can also see the locations of the 4 ZDX structures here on the in the blue points. So as part of there's also been targeted AIM sampling done between 2022 and 2024 here, and you can see here in red the plot centers for those sampling locations. And as part of our larger project with BLM, we've started delineating polygons for AIM sites that represent the plot's spatial footprints. And these we can use in remote sensing. So you can see here on the right, these red polygons represent the footprints of the AIM locations. If we look a little bit more at the AIM data, we can see that there were intended to be 3 sites, one in the original 2015 springhead up here, one within the new 2023 exclosure, right in the middle, and one below the new exclosure down here. Unfortunately, this lower site was initially placed halfway within where the fence was ultimately installed. So it was moved after it was initially sampled, and so that site has changed between 2022 and 2024. For this analysis, we looked at several indicators of wetland conditions, including total foliar cover, perennial forb and grass cover, hydrophytic cover with facultative species, hydrophytic cover without facultative species, and a community-weighted mean wetland score based on species composition. And for all these are taken directly from the field AIM data. If we look first at the site within the 2015 springhead exposure, we can see some noticeable jumps and improvements in some conditions in 2022 and 2024, with 2022 in purple and 2024 in yellow. Particularly noticeable jumps in perennial form and grass cover, as well as hydrophytic cover, and to a lesser degree with the wetland score. We look at the middle plot here, which is where the 2023 exposure is. We see sampling there occurred in 2023 in blue and 2024 in yellow, and we see kind of generally increases across all our condition indicators between those 2 years, before and after the fencing went in. Interestingly, if we look below the exposure, even though this site did change, but assuming that the sites are comparable, we can see that between 2022, again purple, and 2024 in yellow, we see declines in most of the metrics that we looked at. So while these field metrics are quite informative, we're limited with only 2 years of data and little context for how these measures fit within a longer time period. So to get at least partway to that understanding, we can turn to Climate Engine for more information on the site's historical context, recent conditions, and we could also and trends since BLM took ownership. And then we can also use remote sensing to help look at how can we help support inference that we can draw from this 2 years of AIM data as well. So we're going to switch over now to Climate Engine and do a little demo looking at some of the ways that we can use it to develop this historical context and inform our understanding of the AIM data set as well. Okay, so here we are in the Climate Engine app, and the first thing we need to do is find our location. So we're going to go down here to Rowland Spring, Nevada, click Center Map, and assuming this works right, we can zoom right in. And here we are at the Rowland Spring location, which again, if we zoom out a little bit, we can see it's right on the western edge of Nevada, near the California border. We can see it's a pretty small system here. And so one of the things we might want to just do first, we talked earlier in the training in the workshop about different mapping extents, and we could just look at here different mapping extents and see how well they represent this system. So we can see here up top is the spring head and then moving down into the drainage way. So we'll go up here to map overlays. The first one we'll test is the National Land Cover Database. We'll click that on. This may take a moment. Okay, and if we go down here to our legend, we can see that this whole area is being mapped either as shrub scrub or as grassland herbaceous. So it's not really picking up that there is a riparian wetland system here. Next, so not very useful for what we're trying to do. Next, we can look at the National Wetland Inventory. We'll give that a second to load. And we can see here it actually does this has been pretty well mapped in terms of springhead. And then we've got some mapping of the creek down here, but it doesn't fully capture the vegetated areas. It does an okay job, but we're not going to use it today. But it's something you might be able to use, especially for the springhead itself in the future. And then finally, we'll look at the valley bottom extraction tool, which we've talked about earlier, and which maps in a geomorphic picture of the valley bottom. And what we see here is that it doesn't do a very good job with the springhead, which is fairly common. Those are kind of hard for this type of mapping to pick up fully the impact of a springhead on kind of a vegetated area, a wetland. But it does, has this kind of expansive view going downstream where it's capturing not just that small drainway, but also a broader, valley bottom as well. So that might be important, a useful depiction if you're interested in not just where the current drainage is, but also in what's happening across the entire valley bottom. So we're not going to rely on these today, and so we'll instead use the custom polygons that I showed that are depicting the plot footprints for the AIM data sets. So I'm going to go back to none here, and then we'll come back. So we'll come back to this. So next, we're going to look just at the fire perimeter. So we can look at here, pull up for any given year the fire perimeters. We do know that the fire that happened here happened in 2012. So just if we wanted to see kind of where that fire was, we can click that on. We'll zoom out a bit, and you can see that the very large extent of the Rushland fire that occurred in August 2012, and that we're right in the middle of the kind of northern portion of that fire boundary. So that's some useful context as well that we can look at. Now we'll turn that off as well. And then, something else we might do just to kind of explore this site is look at some of the base map imagery. So here we can use the NAEP imagery, and we'll come over here to the base maps, drop down to NAEP. The first year here with NAEP is 2006 that we have NAEP for, and so we'll turn that on. You'll see it'll tell us down here if you pick which years we have NAEP imagery available for. So as that loads in, we can see, we can see the spring head, we can see where the pond is, and we can see some vegetation moving downstream. If we go to the next year, 2010, we can see, how much that changes. Every NAEP year will be somewhat different because it can be flown different times of year, and we'll just sometimes the imagery will look different. But we can see, the system is still kind of, you can see the system here to some degree. It's hard to see. The next year we might want to look at is 2013, which is right after the year after the fire. You can see if we see any changes, and we do see, both reduced vegetation here in the spring head area, as well as, a lot of the trees in the surrounding area have been burned as well. Once we get to 2013, we can switch over to the false color because we now have near infrared in NAEP, which can really help us see the presence of vegetation. And so you can see here in red, the very limited vegetation that exists at this site after the fire. We will just pick one more year here, 2019, see kind of what looks like after recovery, after the initial fencing went in at the spring head, and we can see much more expansive vegetation in that area above where the spring head exposure now is located by 2019. And then we can see downstream, there's some areas that look pretty green. As we'll get to, 2019 was also quite a productive year and a wet year with a late summer with a lot of late moisture. So one thing else we can look at in the base imagery that can be really helpful is the 3-depth data, which is coming out of the 1 meter LiDAR data from USGS. And we can look at slope, which can really help us understand something about the geomorphology of the system. And here we can see here how the spring is emerging from this cliff band on the western side. We can see the channel forming here. We see the pond, and we can kind of see the channel moving downstream as well. So this gives us a sense of the geomorphology system. You can also see pretty clearly where the road is coming up this way. That's right along the site. So this again kind of provides some additional context and understanding of the system that we might be interested in. Okay, so we'll turn those off. And now that we've kind of got a little better sense of how the system and kind of what the imagery looks like over some years, the next thing we might want to look at is start to look at the kind of the spatial patterns in vegetation. So we're going to make a few maps here. But before I do that, I want to load in the polygons that we're going to use today because they can be helpful context for understanding what we're looking at in the map. So we're going to move over here to make a graph from make map. We're going to go to region and pick custom polygon from shapefile. When this pops up, we'll see that there's some detailed instructions. We're not going to spend a lot of time looking at those today, but this is really helpful for helping you understand how you can create a shapefile that'll work when you upload it into the system. So look at that if you're doing this yourself. And then we're going to go choose files, and I've got my shapefile here. We'll load that in, and then we want to pick the column name that has our site name, which here is called site name. And so now it's a little hard to see with this map, but you can see we've now got 4 polygons here for the 2015 spring head exclosure site, the 2023 exclosure site, and then the site that's below the exclosure. So the next thing we're going to do is come back over to make map. And we're going to look a little bit at some of the vegetation data. So we're going to use NDVI, which we talked quite a bit about today. And we're going to first look, we're going to go here to type remote sensing, Landsat, and then we're going to look at we'll look just at this past June through August. Again, we've talked about that the summer period is a good time to be looking at kind of riparian and wetland systems. And we're going to calculate NDVI. We'll let that load in. And now, we can see kind of some patterns that look where we see higher NDVI around where the spring head is and where the drainage way is. If we go over to click make graph, you can start to see the polygons plotted on here. And one thing you'll notice is this site is fairly narrow and fairly small. And so, Landsat is 30 meter pixels. And so we don't have, our spatial resolution is relatively coarse compared to this site. So it's just, because of that, we're going to also look at Sentinel-2 data as well and just see how that compares, which is 10 meter data. We'll go to Sentinel-2 SR, surface reflectance, and then we're going to compute, hopefully we're going to go back over to the map, and we'll compute map again with Sentinel-2, just get a sense of what more we can pick up with a finer resolution data set. Give that a second to load in. And we can start to see that, we're seeing some finer resolution here. We can see more discreetly kind of where the spring head is. And, so you might take away from this that, in general, Sentinel-2 would be a more appropriate data set to use here because of the size of the system. But the downside of Sentinel-2 is that it only goes back in this location, 2017, usually 2017 or 2018, depending where you are. And so we have a limited temporal window. And so, the next thing we might want to do is start looking at trends over time to better understand the context of the system. And so for that, Landsat is much better suited. But before we do that, we might want to just check, how well does Landsat and Sentinel correspond? Do we feel like Landsat, even though it's kind of coarse, can it still help us understand what's happening in the system? So I'm going to go up here to help us just check this, and we're going to create a 2-variable scatter plot where we're going to compare Sentinel-2 data, which we'll have here, and we'll just do again the June through August period. We can just change this to June, July, August, which will be the same. And we have 2017 to 2015 here. And now we'll go here to variable 2, and we'll pick the Landsat and DVI. We'll again use the same period of time, June through August, in the same time window, and we'll click. It will do this just for the spring head exclosure, which is this polygon right here. We'll say how comparable are these to each other. So we'll compute this time series. Okay, and so now we have this loaded, and so now here we have NDVI from Sentinel on the x-axis and Sentinel and NDVI from Landsat on the y-axis, and we can just quickly put on a regression line, and you can see we've got pretty strong correspondence here. So that gives us some confidence that we could still use Landsat, understand something about the system, even though its spatial resolution is a little bit coarse, perhaps for some of these systems. So with that knowledge, we can kind of come back to our map feature here. We'll come back here to map, and we're going to go use Landsat and DVI and start looking at some trends. And so the first trend we'll look at is the slope of the trend, and we're going to look at the historical period from 1984 until before the fire. So what was happening in the system before that fire came through. And we'll zoom out a little bit here. Oops, that's too much. And we'll click Compute Map. We'll go this a minute to load in. Okay, and so what we see here in blue are positive trends in DVI, and this again is that June through August period, and then we've got in red negative trends. And so if we put this back on our polygons back on here, so we can just look at it. Sorry, it's some zoom issues, but we will see, and we put the map on, we can see that there seems to be potentially in this initial period some negative trends. But we might want to check just how certain are we about these trends? How confident are they? So we'll click back here to map, and then we can do a p-value mask here and say, well, let's look at it within a p where we mask out any location that has a p-value above 0.2 to kind of just look at the confidence level we have in these trends. And what we'll see as this loads in is those areas that showed those negative NDVI trends. They're fairly uncertain. We don't have a high p-value for those trend slopes, and so we can think what that is. There's maybe some weak evidence that there was trends, but there's not strong evidence of trends in that pre-fire period. Now we might be interested in looking at the post-fire period, so we're going to do 2013 to 2025, and we're going to leave that 20%, that 80% confidence mask on. We'll click Compute Data. We'll give that a moment to load in as well. And what we'll start to see here is a lot of blue, so a lot of increasing trends, and it's pretty saturated. So, what we're kind of seeing here is we've got an issue with the scale bar. We don't get high enough in the trend values to really see differences. So let's come over here to our computed map, and we're going to just change our scale to negative and positive 0.02 NDVI per year. We'll update the map and we'll see how that changes what we can see. Okay, so now we have a much clearer sense of the patterns. We see, more significant, larger increases in NDVI, and if I can add our polygons back on, that's right in the spring head exclosure, and then going down as well into some of the areas below as well. So we're seeing some patterns and increasing NDVI, especially at the spring head exclosure. We might zoom out a little bit and just see if we can get the map to load. And it might not load today, but one of the things you do see is there are some broader patterns of greening in some of the other systems here too. So, it may be related to some of the exposures into the restoration, but it also might just be related to recovery kind of in these wetter landscapes post-fire as well. So, okay, now we've got some sense of the trend information. So the next thing we're going to do, we're going to come back over here and we're going to think about what else can we learn about these systems from kind of from their perspective of their remote sensing data. So one of the things we might do, and Eric already showed some similar plots earlier, is do kind of a pre-post assessment of the spring head exclosure, where the exclosure was put in 2015. You might understand, how does NDVI compare before and after? We have these plots here that on the left that shows a relationship between a drought metric and NDVI, and I'll go over quickly again how we can make that figure. And then on the right hand side, we've got just a time series. So let me make that figure and then we'll talk about what this is showing us. Okay, so to make this figure, come back to our app, and then we're going to keep the two variable scatter plot on. And now we're going to still have our custom polygon, and we're going to pick the spring head location. Now we're going to go to variable 1. We're going to change this to climate hydrology. We're going to use GridMet, which is GridMet drought. And we're going to pick the end of we're going to use a 270-day SPI value, which will capture most of the, and we're going to do this kind of at the end of the water year. We'll do it for this period, June through August. And so then we're going to look at this. We're going to have compare two data ranges. So we're going to look pre and post exclosure. So I'm having some issues here. Let me come back to this. So we'll go to the remote sensing. We're going to change this to Landsat. And now we'll kind of have the mean value over June through August. And we're going to look at this from 1984 until 2015, before the exclosure went in, and then 2016 through 2025. And now let me click back here, and that should be fixed. So that's our time period we're looking at. So we have these two different periods that we're going to do this analysis for. We'll click compute time series. And so it's going to be pulling these averages for both the GridMet drought, the SPI metric, as well as the NDVI from Landsat for these periods, and we'll be creating a scatter plot of annual values. And while that loads, as we've talked a little bit about, what this plot helps us do is isolate the impact of some kind of intervention while accounting for the relationship that exists between vigor or productivity of vegetation and drought or climate as well. So it allows us to kind of remove that effect and look for changes, either increase or decreases relative to the historical baseline. So now we have a regression line here, and then we're going to add in the confidence bands for the baseline period here. I'll turn that one off. Okay. And so what we see here is on the x-axis, that SPI, the drought metric, and on the y-axis, NDVI. In the red triangles are the baseline period, with the baseline relationship between the two as a red line, and the prediction intervals in the shaded area. And then we can see what NDVI looks like in the recent period post the intervention of the fencing, And what we're looking for here is, does NDVI kind of plot within the bounds of the prediction interval or outside those bounds? And if it's outside the bounds, that provides us some strong evidence that there's been a shift in the system compared to the historical baseline. And so we do see that, most of the blue dots are above the line, above the prediction interval. So we've seen, an increase in NDVI for a given, annual climate condition since the fencing went in here, suggesting, potentially the fencing had an impact on productivity in the system. If you look at the time series data here too, we see something similar. Now, another way we might look at this is thinking about this from a perspective of a reference compared to treatment assessment. And so, we might see this relationship, but if we also see that same pattern happening at a reference site, then it might be something else might be driving this pattern, not the intervention. So here we've got the same plot on the left-hand side for the spring head exposure for the 20, and then we've got the location below the new exposure for the same time period, and we can see that there is some in the below exposure. We have seen some higher NDVI values since 2015 relative to the historical baseline, but most of the points are still plotting within the kind of the bounds of the prediction interval historical period. So seems like there's been some shift there towards higher NDVI, but not as significant as we're seeing where the fencing went in. So again, that provides some additional information about whether or not that intervention had an effect. So, yeah, we also, might want to use this analysis to help understand a bit more about what we're actually seeing in the AIM data and what we know about, when that data was collected and what that tells us, how, about what these patterns are that we're seeing, and we are seeing some fairly large patterns here between 2022 and 2024, or even 23 and 24. So we're seeing large shifts in the community composition and the cover. So we want to understand a little more what's driving that, if we can, using remote sensing. So the first thing we might want to understand is, how comparable are the AIM sampling dates? And so we could do that with, one way we could do that is think about, well, what was the climate like when sampling occurred across different years and how comparable are those? And we can see, 2022 was somewhat of a drier year here, that you can see that here as a negative value as for 270-day SPI. And it came on the heels of 2 drier years before that. So it was the third dry year in a row. 2023 was a relatively wet year, and 2024 was also a relatively dry year, but did come on the heels of a wetter year, so there may be some recovery because conditions hadn't been as dry for as long. We also might want to understand, how comparable are they in terms of timing of sampling. Sampling for AIM doesn't happen at the same time every year, and so we could look here at creating a plot where we look at the kind of the phenology of NDVI across the season, and then plot on top of that when the AIM sampling occurred based on that kind of phenology, the NDVI phenology for the vegetation in those locations. And so here we've got plots that show, this is using the harmonized Landsat and Sentinel data set, which provides us, the best temporal coverage that we have for 2022 in purple, 23 in blue, and 24 in yellow. And we've got these stars, or the timing of when AIM sampling happened at each of these sites. So I'm going to quickly show you how to make a plot, and then kind of how you can pull this data in Climate Engine, and then show you how you download that data. These plots are actually made in R, and so one of the things that you can really do to kind of level up your game using Climate Engine is to generate data with it, and then pull it down into your favorite programming package or plotting package, and start making your own plots with that data. So we'll come back to Climate Engine here, and I'll just quickly show you how to make this. So this is just a single native time series, and we're going to use, again, we'll look at it for the Spring Head site, and then we're going to go to remote sensing. It's HLS-SR, it's a harmonized Landsat Sentinel data, and we're going to pull it for 2022. Circle 1 until the end of 2024. Yeah, We'll compute time series. And again, you know, some of these requests can be quite a bit of data, so it can take a while. Sometimes you do need to reset things too. If you're seeing a lot of slow loading, then sometimes it's valuable to kind of reset the app and try again. I will give this in a minute. I'm also going to see if I can click through and have this load. Okay, so here we go. So here we have the the full phenology for each of these 3 years NDVI. You can see kind of we have quite a bit of data here because of the harmonized. It's using Landsat and Sentinel, so we've got quite a number of days that we've got data. It is kind of noisy, and so one thing we can do is create a running average. We'll do that for a week, and so now we have kind of a smoother version of these data sets. The next thing we want to do here for creating the plots I made is we want to download this data. And so here you can go over to download it as a CSV. And if I open this up, we'll see we've now got a CSV of those data. So you can pull that again into R or Python, or do a plot in Excel and kind of create custom plots that you can't make in the Earth Engine and the Climate Engine app. So again, really valuable for kind of moving to the next step of analyses that you're interested in. Here we have these plots here, and so one of the things you can see in these plots, if we look at the spring exposure, sampling occurred about the same time of year in 2022 and 2023, and they had fairly similar phenologies as well those 2 years. The same thing that happened in the newer exposure happened in 23 and 24, and it looks like it happened much earlier in the year in 23 than 24. And also that sampling, that 2023 was a much different year. It had, a later phenology, things greened up later, and it had a much more extended peak, a higher peak, and a much more extended greener period as well. So there's some substantial differences in terms of, what the vegetation looked like in those 2 different years, and the timing was also different. And so that might kind of raise some questions about how comparable are the findings from those 2 years. You need to think about that when you analyze those findings. So, kind of to wrap things up a little bit, we can then think about how could we combine these plots, some of these plots we've created, to think about what we've learned together, and how well do the findings compare to each other. And so if we look at the Springhead site again, we can see that again, kind of, this is the 2 years where there's AIM sampling, 22 and 24 on this plot. And we can see that they were fairly, similar NDVI years. But we did see these big changes in the Springhead metrics here for perennial foreground cover and hydrophytic cover and the wetland score. And so if you look, a little bit at some of the actual data here, one of the things you learn is that in 2022 at this site, they found quite a bit of cheatgrass. And in 2024, they didn't find much cheatgrass at the site. And so, one of the things that you can't really see here in the remote sensing data, you don't see much change, and you really don't see much change in the total folio cover. But there does appear like there was a change in those 2 years, across those 3 years, in the species composition, and that's something that can only come out of AIM data. And so, again, kind of just to highlight, these data streams provide, complementary information that can provide, the remote sensing can provide context for understanding the AIM data. The AIM data can also help us better understand, go maybe a little bit deeper than the remote sensing data and understand things that you can't capture from remote sensing. NDVI can capture overall, greenness, and to some degree whether or not there's kind of more healthier vegetation at the site, but it may not always be able to capture whether or not that vegetation at the site is native species or are non-native species. So I'm going to kind of wrap up there. I hope that this case study helps you see the value of how you can use Climate Engine in kind of broader workflows, how, increasingly as we have more AIM data available to us, I think there'll be opportunities for really integrating more remote sensing with AIM data sets and other similar field data sets. And so, happy to take some questions if there's time for questions. And yeah, appreciate your time today. Thank you.
Awesome. Well, thanks, Alex, for a fantastic demo. I think being able to pull in the AIM data alongside remote sensing data, that's how we want these data to be used, I think, by BLM. We talk a lot about incorporating remote sensing into a multiple lines of evidence approach. Being able to, have that skill to interpret what you're seeing in the field data and what it can tell you alongside what we can see in the remote sensing data, I think is a really powerful combination. Remote sensing will give you that information across a landscape and through time, where field data is going to give you much more detailed information about vegetation, about soils, things like that. So they're really meant to be complementary. So as we move to close here, obviously Alex and I have re-recorded these demos. We had some technical challenges during the initial delivery of this training, and so we wanted to capture the demos in full. But I'll walk through these kind of closing materials for you. So we have lots of published information online. You can visit our website at climateengine.org. Future sessions in this series are going to focus on our reporting website at reports.climateengine.org. So be sure and check those out if you're interested. Our support site has a lot of different material, information on specific data sets, more demos in the Climate Engine app, workflows that we've developed for BLM. We have API documentation. We have our YouTube channel. We're active on LinkedIn. So there are lots of places where you can find us. If you're applying Climate Engine in environmental assessments, land health assessments, these types of processes, if you're able to tell us about that, that's super helpful. We can then, have a better accounting for our own reporting of the types of ways that Climate Engine is being used. And so we have a form to help you do that. I encourage you to take a look at that form and fill it out. It should take 5 minutes, and we would very much appreciate it. If you found this training helpful, or if you found it confusing, or however you found it, we really value the type of input we get through our surveys after these trainings. So just encourage you to fill that out. We really do look at those responses and use them to help to guide our materials going forward. This is no longer relevant if you're watching the recording, but there was an office hours hosted by Tim Asal. And if you're interested in learning more about these types of trainings and these types of tools, and you work for BLM, then Tim Asal is a really good person for you to be in touch with. You can find him in the directory. And with that, I want to thank you for attending this training. We've really enjoyed being able to give this series of trainings for BLM. And for us, this is really where the rubber meets the road, and we can better understand how staff are using some of these tools, the types of features you want to see. And so we just really appreciate your participation and attention, and hope that we'll be able to stay in touch with you and learn from the different ways that you're using Climate Engine out in the world. So thank you.